Good afternoon, everybody. My name is Patrice Chartrand. I am professor at Polytechnique Montreal and a co-developer of the FactSage software. With my colleague, Dr. Ayman Gheribi, I'm very happy to present you advances in FactSage 8.1 in how in Equilibre we compute the thermal conductivity of phases and of phase assemblages. This is coming from a project with the Rio Tinto Aluminum, Polytechnique Montreal, and the University du Québec à Chicoutimi in Canada for developing a model for the thermal conductivity of a solidified crust of molten cryolite that is must be present in industrial oleoelectrolysis cell for the production of primary aluminum. This solid crust is essential to be there for the protection against the very corrosive electrolyte, molten fluorides that are dissolving alumina at around 1000 degrees Celsius. So the crust thickness must be optimized to put anodes there, and it affects the dynamic heat balance of the cell, which roughly has a heat flux of 800 kilowatt. Different postmortem structure shows that this solid crust is made of several different phases, mostly fluorides, but some oxides of alumina, corundum, beta alumina, gamma alumina, but also some carbon, and it contains sometimes quite a lot of porosity due to the presence of CO2 dissolved in the electrolyte. So we want to provide a company with a model. We wanted to provide a company with a thermal conductivity model for this side ledge, which is related to its thickness. So basically, we need a model that is able to compute phase properties, microstructure properties for the thermal conductivity. But we have to do assumptions here. First of all, we will be working with insulators, non-metallic phases, because the electronic contribution to the thermal conductivity is not yet developed in the model. And we will be working with pure stoichiometric solid phases, no solutions. These are still current limitations of the model. And we assume that the Equilibre module of FactSage, with the proper databases, will provide a very good estimate of the volumetric fractions of the phase. This is their mass distribution at equilibrium and their volumetric properties, giving the volumetric fractions. These calculations with Equilibre can be done under normal equilibrium mode or Gulliver-Shall cooling, for example. As the microstructures strongly affect the thermal conductivity, we need simplified models in order to evaluate the microstructure, impact on microstructure. Specifically, the absolute limits of the parallel and series microstructure, but mainly some random type of microstructures with spheres or shape factors to be taken into account. So the scientific approach consists in 5 steps. The 3 first steps are to compute the thermal conductivity of a pure phase as a grain of diameter d at a given temperature T and for an intragranular porosity inside the grain that is fixed. So once we have these 3 functions of temperature, grain size, and intragranular porosity, one can assume at this point we get a very good estimation of the thermal conductivity of a grain of a pure phase, which is constrained in diameter and has some porosity. Step number 4 and 5 is actually to introduce mixtures of grain inside a microstructure, and that can include intergranular porosity, which can vary quite a lot. This is step 4 for the intergranular porosity, and step 5 is actually the impact of the volumetric phase fractions as computed by Equilibre. So what the model will provide is the maximum and minimum limit value of the thermal conductivity given by the parallel and series mode when you have different phases in different grains with different sizes. However, we want to provide the best estimate using EMT approach, effective medium theory, And this effective medium theory goes very well with the Hachin-Strickman upper and lower recommended value limit. So basically, the EMT value is always between the Hachin-Strickman limits, which are always between the minimum and maximum values. So in order to compute the thermal conductivity of a pure solid phase as a function of temperature, we need information about that phase, its structure, its molecular weight, its Debye temperature, its Gruneisen, its average volume per atom, and the number of atoms per primitive cells. Once we have this, with this theoretically derived function, we can compute the variation of the thermal conductivity of the phase, and it's an inverse function. Please note we have a correction term here, F, which equals 1 in all cases except for chlorides. For chlorides at very high temperature, we get a correction function, which is an exponential of the Debye temperature over T. So we can compute from these values that can be obtained from the FT calculation, the predicted thermal conductivity of a pure solid. This is the phase of alpha corundum here. You can see our calculated curves with some experimental points and the FT calculation. So we did this for 488 pure solids. All the colored parameters here are stored in the FACT database, FACT-PS database, with subsets in other specialty databases like FT oxide, FT salt, FT all, and others. The second step is to derive an expression for the thermal conductivity as a function of the grain size. For big grains, the grain size has no impact, infinite size grain. But when we go below 150 microns, we start to have a small deviation, and below 10 micron, 1 micron, it can be very large. Here you can see the case of silicon nitride at 300 degrees Celsius. When the grain size is infinite, you get the the green line. And when you take into account the grain size with this function, you get an important deviation, which can half or even lower the value of the thermal conductivity. It takes into account the grain size, the corrective term, and the sigma t function, which is a phonon characteristic length, which is computed with data that we already have or calculated previously, like the Debye temperature, the Gruneisen parameter, or the thermal conductivity of the single crystal, thermal expansion and capacity of the phase. Now, the third function related to the phase is the intragranular porosity, as highlighted here into this little picture. Here we basically have dilution of the thermal conductivity, linear dilution, as function of the intragranular porosity. It can be made nonlinear if the value of the M parameter at the denominator is different than 0. This is an effective parameter that is accounting for pore size and dispersion within the grain. And it's a parameter that is not stored, but the user will have to provide, 0 being the default. With the three first functions, we get the thermal conductivity of our grain at the temperature T and internal porosity. Now we want to make a phase assemblage of these different grains at the same temperature, even though we compute the thermal conductivity for a temperature gradient. But we have to take into account the impact of the intergranular porosity, which can be very strong, and the impact of the volume fractions of the different phases. So our model takes into account a critical porosity for the intergranular porosity. So it's a critical function where you get an inflection point given at the critical porosity, which is a user-defined parameter. We recommend a value of 0.16 by default. Most values we found are between 0.11 and 0.23 volumetric fraction, but the example here with the sintered tungsten metallic powder, we have a critical porosity of 0.2425, as you can see, and there is an inflection point in the curve of the thermal conductivity as a function of the porosity here. The fifth function is basically the model for the microstructure in terms of the volumetric fractions of the different phases. So we have two absolute limits. The parallel type of microstructure will give you the maximum thermal conductivity limit of the phase assemblage, given you have several phases N with a volumetric fraction Phi with different thermal conductivities as computed with the previous functions for every phases. So if the values of Ki varies a lot, the parallel mode is always the highest thermal conductivity, while the series mode is the lowest value, which is related to an inverse function of the thermal conductivity. The expected value of the microstructure must lie in between the two. And here we recommend the EMT approach, the effective medium theory of Landauer, 1952, where we basically have to compute from this equation here. We're solving this equation with the thermal conductivity of every phases I and their volume fraction, and there is only one value of the effective thermal conductivity of the phase assemblage, which will give a zero value for this function. And this is what we solve numerically. It's quite simple. And the Aschen-Streckmann upper and lower limits given by these two equations are basically also given to you by the model. And they are always bordering the EMT recommended value, quite narrowly actually. So the source of data for the implementation into Equilibre module of FactSage is many of the parameters are actually already stored in a compound databases. And these parameters are all related to the three first functions, basically the pure phase. However, for the microstructure, we need extra information. We need the grain size, we need the different porosities, including the critical porosity. And if we have an intergranular porosity, we need a value of M for the denominator, which is usually 0. So we created a new microstructure module in FactSage, which is stored in your main FactSage directory. It's a direct executable. If you double click on it, you can store the values here. Click on the Save to File button. And you have to do that before performing your calculations in Equilibre. Now, the other step for the calculations are highlighted as follows. So we already have parameters in the compound database, which are relevant for the computation of the thermal conductivity. And with the microstructure module, the user must fix the 5 different values that are there. Once this is stored, you go to Equilibre, you set up your reactants, your masses, you set up the temperature, the pressure, any alpha values, beta values, target. But at this point, you only have to select the pure solids and maybe gas also. But the thermal conductivity will be computed only for the pure solids. So once you click on Equilibre, after clicking on Include molar volume and Calculate physical properties, you click on the Calculate button, and Equilibre will compute, as usual, the masses and volumes of the different phases at the given temperature. Then there is a dynamically linked library called physprop.dll that is using the stored parameters from microstructure to compute the thermal conductivity of the phases, which will appear in the Equilibre output, and will store in the physprop t-thermosystem results.ini file in the FactSage directory the 5 different thermal conductivities that were presented at the step number 5. So the parallel and series limit, the maximum and minimum Aschen-Streckmann value, and the EMT recommended value. So as an example, we will take a refractory lining. So on the 488 compounds which we evaluated, there are many oxides. So we'll have a refractory lining composed of 60% silica, some corundum, and impurities of rutile and hematite. And what I want to highlight here is we will use the Equilibre output with 2 different microstructures, one involving a working layer with grains of 100 micron, intragranular porosity of 10%, intergranular porosity of 10%, and a critical porosity of 18%, and M equals 0. And below that layer, there will be a thermal insulation layer with the same characteristic but a much higher intergranular porosity of 40%. So at this point, I will go in the equilibrium module. But before going to the equilibrium module, I must go to the microstructure module to fix the microstructure characteristic. So the porosity intragranular would be 10%, intergranular 10%, 18% critical porosity, M equals 0, and grain size will be 100 E minus 6 microns. And I will save this. Now you can go in the equilibrium module, and in the equilibrium module, you enter the different amount of the refractory constituent. We will fix the temperature between 300, 1000, and 100 degrees Celsius. I'm selecting all the pure compounds of these four compounds, and I make sure I click on Use Volume and Physical Property Data. Now I can make the calculation for the working layer of refractory. And as you can see, as function of temperature, equilibrium is computing the phase fractions and their volumes, and the FISPROP DLL is providing the thermal conductivity of the four phases as function of temperature, as you can see. Okay, and these values are computed for the given grain size with the 10% intragranular porosity. Now, the results of the microstructure thermal conductivity will be obtained in the FISPROP T-thermal system result INI file. If you double click here, you will see the characteristic of the calculation in terms of the grain size in meter, the intragranular porosity, intergranular porosity, critical porosity, the value of M, the temperature of every calculation, followed by the pressure, and also you will get the total volume of the system. Total porosity is computed, and in the end, you will get 5 series of thermal conductivity based on the EMT model, the Aschen-Strickman higher limit, Aschen-Strickman lower limit, and you can see that the EMT value is lying closely between the two Aschen-Strickman limits, and at the end you get the parallel conduction and the series conduction for the microstructure for all the computed temperatures. Please note that the values are roughly around 8.5 watt per meter Kelvin. If now I go to the microstructure program and I put an intergranular porosity of 40% and I save, and I will go back to equilibrium and reperform the calculation, I will get the same values for the thermal conductivity of all the phases at the same temperatures, with the same phase fraction. However, the intergranular porosity being much higher, we will see that the result now in FISPROP T-thermal system result.ini are much different. If I scroll down to the EMT recommended value, I get values below 1 before I had 8.5. This is the Aschen-Strickman upper limit and lower limit, and again this value is in between, and we get the absolute higher limit of the parallel mode or the series mode here. I go back to my presentation. Sorry. And as you can see, there is a very big difference in the thermal conductivity with the same phase assemblage except for the porosity, going from 10 to 40%. So as a conclusion, Thermal conductivity model was implemented in the equilibrium module of FACSAGE for the calculation involving pure compounds insulator. These are oxide, carbides, nitrides, fluoride, chloride, some nitrates, and so on. An equilib permits the calculation of the individual grain thermal conductivities for the different phases as function of the temperature, grain size, and intragranular porosity. However, the FISPROP DLL permits also the calculation of phase assemblage. This is stored in the T-thermo system result INI file that I showed to you. It's using volumetric phase fraction and intergranular porosity and the EMT approach of Landauer, 1952. We're still working on this. We are implementing the impact of solid solutions. We already developed the mixtures on a one sublattice. So we did it for NaCl, KCl, and other salts. And in the coming years, we will be developing it for multi-sublattice solid solutions. I thank you a lot for your attention. I'm ready to answer your questions. Thanks.